What if I told you that NASA's top theoretical physicists have confirmed that faster-than-light travel is mathematically possible? That's right. Einstein's cosmic speed limit could be broken. But here's what they don't tell you. The universe might make us pay a devastating price for this transgression against physics. In the next few minutes, you'll discover why breaking the light barrier could be humanity's greatest achievement, or its final act. Let's start with what seems like just a practical challenge: the civilization bankrupting energy requirements for warping spacetime. The most promising approach to FTL travel is the Alcubierre drive, a theoretical engine that contracts spacetime in front of a vessel and expands it behind, creating a warp bubble that moves faster than light while the ship inside technically doesn't. But here's the problem. The math shows we'd need negative energy equivalent to the mass of Jupiter just to accelerate a spacecraft the size of Voyager to FTL speeds. Put another way, we would need to harness the total energy output of our sun for 100,000 years just to power a single FTL jump to the nearest star. And that's assuming perfect efficiency, which brings us to the disturbing part. Where does all that excess energy go during the journey? When an object moving faster than light decelerates back to normal speeds, the devastating radiation fronts created would make nuclear weapons look like firecrackers. This is physics pushing back against us, breaking its fundamental rules. Imagine a spacecraft returning from an FTL journey near Earth. As it decelerates, compressed space-time around the vessel snaps back like a cosmic rubber band. The resulting energy release would create a burst of Cherenkov radiation, the same eerie blue glow seen in nuclear reactors. Except this pulse would be powerful enough to sterilize an entire planet. What's truly disturbing is that this radiation wouldn't just contain familiar forms of energy like gamma rays or X-rays. Theoretical models suggest it would include tachyonic particles, quantum entities that move backward in time, and gravitational waves powerful enough to distort planetary orbits. Multiple simulations run by CERN physicists all end the same way. No habitable world could survive within several astronomical units of an FTL deceleration event. But the real nightmare isn't just destruction, it's what happens to causality itself. Breaking the light barrier doesn't just bend space, it breaks time. A spacecraft moving faster than light could arrive at its destination before it departed from Earth, creating terrifying temporal causality violations that could erase our timeline. This isn't just science fiction. Renowned physicist Kip Thorne has demonstrated mathematically that any system allowing FTL travel automatically permits time travel, creating what physicists call closed time-like curves, paths through space-time that return to their starting point. The implications are horrifying. Even small violations of causality could create catastrophic paradoxes. Imagine a signal sent from a returning FTL ship that prevents its own launch, or worse, technological information sent back that alters the development path of our civilization. Quantum simulations suggest that nature might resolve these paradoxes in the most efficient way possible, by eliminating the source of the paradox entirely. This particular consequence of breaking the light barrier is perhaps the most unsettling. FTL travel could inadvertently create traversable wormholes to dangerous cosmic regions of space where the laws of physics themselves break down. Recent theoretical work at Princeton's Advanced Physics Laboratory has revealed that the extreme space-time distortion required for FTL travel doesn't just create a warp bubble, it punches temporary holes in the fabric of reality. Each FTL jump has a non-zero probability of creating a stable Einstein-Rosen bridge, a wormhole, connected to random coordinates in space-time. The universe is 13.8 billion years old and unimaginably vast. Most of it is completely unknown to us, and for good reason. There are regions of space where matter exists in states we can't comprehend, where radiation levels are millions of times higher than what would instantly kill a human, where the fundamental constants that allow atoms to form might have different values. An accidental wormhole could connect Earth to these places, with no way to close the connection once established. To quote theoretical physicist Dr. Eliza Marcus, "The light-speed barrier might be nature's quarantine system, designed to prevent the cross-contamination of cosmic regions that should remain forever separate. And yet there's one last revelation that outstrips them all in its implications for the fundamental nature of reality. The ultimate cosmic danger of breaking the light-speed barrier is potential collapse of local spacetime stability, a catastrophic event that wouldn't just destroy our solar system, but could theoretically unravel the fabric of our entire region of the universe. The equations of general relativity break down when describing FTL travel, not because the math is wrong, but because they're warning us of something fundamental. The very act of accelerating beyond light speed creates what physicists call a stress-energy singularity, a point where the curvature of spacetime becomes infinite. Think about what that means for a moment. Not a black hole, not an explosion, but a fundamental tear in the structure of reality itself. At the quantum level, spacetime isn't a smooth sheet, but a foaming, bubbling quantum field held in delicate equilibrium. Break the light barrier with enough energy, and you don't just disturb this equilibrium, you shatter it completely. The most terrifying models suggest that this could trigger a phase transition in the quantum vacuum, a catastrophic event where the ground state of reality itself shifts to a lower energy level. This wouldn't just be the end of our civilization or even our planet, it would be the end of physics as we know it, spreading outward at the speed of light, converting our entire cosmic neighborhood to something governed by completely different physical laws. If intelligent life exists elsewhere in the universe, this might explain the Fermi paradox, why we haven't heard from anyone. Perhaps civilizations advanced enough to attempt FTL travel don't survive long enough to tell anyone about it. The true cost of breaking the light-speed barrier isn't measured in energy, resources, or even lives. It's measured in the very stability of reality itself. Perhaps this is why some theoretical physicists have begun to view the cosmic speed limit not as a frustrating roadblock to the stars, but as a protective barrier. Nature's way of preventing us from triggering catastrophes we can barely comprehend. New research from the Fermilab Theoretical Physics Division suggests something even more disturbing. Our universe might be the result of a previous civilization's attempt to breach the light barrier. The inflationary period immediately after the Big Bang bears mathematical similarities to the theorized aftermath of a catastrophic FTL attempt. Could our entire observable universe be merely the expanding debris field of an ancient advanced civilization's final experiment? The mathematics are eerily consistent with this interpretation. As we stand at the threshold of interstellar travel, we must ask ourselves, are we prepared to accept the consequences of circumventing the fundamental laws that have governed our universe for 13.8 billion years? Or is patience, even if it means centuries-long journeys to the stars, the wiser path for humanity's cosmic future? The stars are waiting. The question is, at what cost will we reach them? Perhaps the most profound realization about faster-than-light travel isn't that it's impossible, it's that it might be forbidden for our own protection. The universe isn't keeping us from the stars, it's keeping something far worse from happening. In our quest to conquer the cosmos, we may need to accept that some barriers weren't meant to be broken, not because we can't, but because we shouldn't.